go. Yeah.
Recognize, ignore gender, just match faces.
Yeah, now that would be, that's terrific. That is great. All right, let's begin, Ian.
Let's begin.
You have the thing, right?
Yeah, I do. With this big button that advances. And look at that.
All right. Hi, I'm Ian.
Hello, Ian.
And you are? This is Ian Philpott. I'm Jerry Nixon. We both are from Microsoft. And we've practiced this quite a bit. So, I'm a software engineer. I come from Atlanta, Georgia, so I'm not one of the Redmond contingent. I'm considered to be in the field. And I travel around and help customers build cool stuff. And then I go out and give talks about it as well, similar to what Jerry does. And we kind of, well, we've done a few of these types of projects together.
Yeah, for sure.
It's been interesting. And if you want to know more about what Microsoft is doing in the artificial intelligence, beyond what we're talking about and beyond what Jerry shared this morning or this afternoon at the keynote, feel free to go out to Microsoft.ai.
What you'll find there is not just information, this is also where you access all the services as well. So like that demo of that app is all using services in the cloud, and to find out more about them, that's where the Microsoft.ai comes from. And it's not just vision, we're going to be talking about vision today, but there's a whole slew around language as well, so that you can turn language into actionable code.
And Common. Have you seen this commercial with Common, the rapper? He's on stage talking about Microsoft artificial intelligence.
Yeah,
it's pretty cool.
It's inspirational.
It is. It's all over my Instagram feed for some reason. All right, so back to us. This is talking about vision and artificial intelligence. We're going to talk a little bit about artificial intelligence, kind of a little bit of a recap of what Jerry shared this morning, and then we'll get into what it takes to do deep learning and vision. Jerry is a Star Trek fan. I am a Star Wars fan. So we are divided here.
Pathetic, isn't it?
I was going to swap all of his pictures out that he gave me here.
It's amazing, actually, when you think about artificial intelligence, like what the enterprise can do, being able to talk to your computer in a reliable way. It used to seem so far in the future, and now you can do it with Alexa in your living room, and it's amazing. It's absolutely amazing. You have Alexa?
But we have droids in Star Wars. You do. Yeah. No, I do have an Alexa. I have too many of them, actually. And, you know, my wife has them set up in like where they can communicate to one another. And like all of them play the same music.
Oh, yeah.
You know, so we were talking 9, 10 o'clock at night, you're down coding, and my Alexa starts playing lullabies. That's sweet. Yeah, it's awesome. Awesome to code by. So let's get into it. So we'll breeze through some of this piece because we talked a little bit about it this morning. But kind of the banner here is for artificial intelligence. And I remember when I was first actually subjected to artificial intelligences a few years ago. I worked at a hospital in the data analytics piece, and we were trying to reduce revisits. And my boss was a PhD in artificial intelligence, and got to learn quite a bit from the late Luke Ging. He traveled back to China and back to the U.S. and spoke all over the world, and I had a good time learning quite a bit from him in this space. And one of the first things that I learned was that we were nowhere near artificial intelligence, and to be very skeptical of it as I go along. But then we progress into the machine learning piece of this, which I found much more interesting and much more realistic. Even 5 years ago, we were closer to this. We were building Hadoop clusters and kind of getting into this distributed data world. And it was pretty neat, but I was very skeptical about it going forward. I think a great example of this is the Roomba.
Yeah.
Right? You turn it on and the thing runs into all your walls.
That's right.
Right? And you're laughing at it and you're like, haha, I'm still smarter than a computer. And then 2 days later, you come back and the thing's chasing you, you know? It doesn't touch anything and the dog's not freaked out by it. That was actually pretty funny, having it, my dog freak out. Anybody have a Roomba with animals? I mean, if you have animals, you need one. They're a lot of fun.
The processing power on a Roomba is tiny. Like, it's not a massive machine at all. And what's amazing is it can accomplish pretty sophisticated three-dimensional machine learning, even in that tiny space. It really goes to show that machine learning, as complex as it is really a straightforward kind of affair.
And then we kind of get in to, well, is this stuff good or is this stuff bad? And it is what we make it, right?
So the bad is, it seems like it's taking everybody's job. The only job you seem to target are the jobs that are repetitive, the jobs that are low tech, the jobs that seem easier, the jobs that are blue collar. That's the initial thought, right? And if you look at technology, this is a crisis for.
I mean, that's just automation in general, right?
Yeah.
And machine learning is ratcheting up automation to a whole nother level where now it can start looking at our logs and start automating fixing problems and things of that nature, which I totally agree. But who wants to sit there and look through a bunch of logs to do a root cause analysis? No one, right? So this tool, this can become a tool for good or for being lazy. I mean, you know, whatever you want. But I look at it as a good thing. And this is one of the main areas that I work in these days, is taking telemetry data, making sense of it, and having machines report in and say, hey, I have a problem, somebody needs to fix me, and this sort of stuff. That is it's predictive maintenance, right? That's a big one.
Yeah, what it can do is it can make it so that you're really good at a job, but you can only scale so much.
Yeah.
If I can make a machine as good as you, then you can be really good at the job and you can do 3 times as much work. I mean, you can look at it like that. You don't have to look at it as something taking anything away. This is really more of enabling you to be able to accomplish more because we have this technology to leverage all the skills you already have.
Just like mathematicians and computers back in the 1800s.
That's right.
Just like when they used to have 3 people and now they've got 1.
Exactly.
Just like that.
That's the scary
No
thing.
comments from the audience.
So we move into kind of the niche emerging kind of part of the market here with deep learning. And we talked a little bit about this already, deep learning being a very important piece to this. And we're going to dive a little bit deeper around deep learning.
That's the scary part of it.
And Jerry shared this morning, and I think this is really interesting what they're doing here, Airbus, in building this wall. I know it seems kind of one of those silly things, but I think the major point here, I think that wall looks like something off of an Alien movie, right?
Or a spider.
What you would envision an alien craft landing and showing something like that being all over the place. It looks kind of weird, right? It doesn't look pleasing to us. But as we move on, I think this one is even more interesting. This is a project out of Microsoft Research. That's not a real bird.
This is the logic that goes backwards from what we already know works. So right now you go to search for a sunset in Google and you say sunset, and there are a whole bunch of sunsets. And it does that not because it knows what a sunset is necessarily, or they're all tagged properly. It's because it's been able to recognize that based on its training. So I can take an image and I can give it a description, and then I'm really searching against that description or set up keywords. This is the opposite of that.
Right.
Yeah, tell us what it is.
Right. So we give it a description, and it comes and gives us an image.
Is it just searching the internet?
No, it's not. It's going through and a machine learning algorithm here, or let's say a deep learning neural network. We give it a set of descriptions. I want a yellow bird.
Small beak.
Small beak,
Black wings.
black wings, it kind of got the black wings. There's a little bit of white in there. It kind of bothers me that it made it so natural, right? But it goes out, it knows what a bird should look like. It knows a bird's habitat even. And it goes out and actually creates what it thinks should be a bird. And that's kind of that first very pixelated piece there.
Now we have algorithms that can recognize if an image is a fake or if an image is real. So we could use that in conjunction with what we're trying to accomplish here. So it draws that first image, and you can see, and I can see, and this algorithm would also know this is a fake. So instead of accepting the first image, we pass the image back to the algorithm and says, that image is a fake, you need to do better. And that's the beginning of the recursion.
Exactly. The cycle that we go through. And that's a key point. And we're going to revisit that in just a minute. This recycling of bits to make them better and better as we go progressively along. And that's what deep learning and neural networks are all about. So to kind of recap, we've got artificial intelligence, machine learning, and then deep learning. Deep learning is where we want to focus for right now. So let's kind of dive in and talk about why deep learning hasn't been a thing until now. Okay, we have the kind of Moore's law. Jerry shared a great explanation, and I'm sure everybody here was there for his talk, so we won't spend a whole lot of time in this area. But 10 years ago, if you're looking at 20, we're about where the 40 is right there, which is kind of weird to have on the graph at that point. We don't have a lot of transistors. I mean, we have I don't even know those numbers.
Yeah.
What's a 10G?
We have, well, the important part is once we get to the what's a gigabyte? Once we get to this limit, we have this gap before we get to quantum computers. That's not really going to be the answer today. So we need to start answering it in other ways. And so jump to the next slide. I'll show this is the specially designed chipset that says I can't put quite as much on a single chip as I want, but what I can do is I can put specific types of transistors laid out. So instead of a general purpose chipset, I can have a specific intention. So this one is meant if you ever take a self-driving car Uber that picks you up, and you see the back is a small data center because its requirements in order to process that much imagery is really high. The power requirement is high, but so is the computational cost, right? And so this chip is intended to solve the problem in a kind of intermediary way by saying, we only have so much stuff, so we're going to make a dedicated chipset to the purpose so that we don't have to put as many things on the chip doing things that are extraneous to the process that's going on. So it's a dedicated chipset. This one is the one for self-driving cars. This is the one for AI on a camera. And it's awesome because it also drops the power requirement as well. And so I can have a general chipset that accomplishes whatever I need in a camera, and it gives me, let's just say, battery life of 10. And then I can put a dedicated chipset, and it gives me battery life of 20 because it doesn't have to do all the extra pieces because it's a general purpose chip otherwise.
And I'm kind of curious, what do you think of this camera? What do you think of putting a camera on and wearing it all day and having it, through doing machine vision, recognize your kids,
Tell you their name.
and take pictures of them, right? So you tell it, I want it to take pictures of my kids and my family, my dog.
I can see it on cops.
Put it on, and you wear it all day, take it off, plug it in, and see what it's actually, I think,
like a
Bluetooth app.
5-minute summary of your day.
Yeah, but it only takes pictures of your kids.
That'd be weird.
So you never have to pull out your phone and take pictures. Oh, they're doing something cute. You're at the basketball game, right? That's the idea behind it, which I thought was kind of interesting and a little creepy. Yeah, here you go. Add this, give this to cops. I got you. All right, so let's get into the deep learning, machine learning, and talk about the questions that we want to answer. And I thought this was great. Jerry showed this to me. I was like, all right, we're definitely adding this because I think this is a great high-level overview of this. So we have the different types of algorithms. The first one is the classification algorithm. It's probably something where we're all familiar with in the vision. Show it a picture. What is it?
The cat video.
Yeah. The next one is anomaly detection. This is one of the things that we want to do in streaming when we're dealing with Lambda architectures and doing streaming data analytics and things like that.
Also used by your credit card company to cancel your credit card while you're on vacation.
which is awesome.
It's machine learning. It's learning, getting better. That's right.
That's true.
The next one is the regression algorithm. We're going to spend a little bit of time talking about regression algorithms, even though they don't have a lot to do with vision. They're pretty simplistic and most people can understand them, so we'll spend a little bit of time with that. Regression algorithms are cause and effect in predicting if I have this cause, what will the effect be in the future, typically. Clustering algorithms, I just did this with one of the schools back home. They were trying to understand where their students were. So we had their addresses, we converted that to lat long and ran it through a k-means cluster algorithm, and it shows groupings of their students around campuses.
And clustering could go one of two ways. You can do supervised and unsupervised clustering where you know what this is, so you get the breed of dog that you want. Or you can say, I'll bet there are groups here. And it'll start to find a group, and you're like, wow, everybody's a Virgo.
Yep.
Or whatever.
And then, of course, one of the most interesting ones that everybody likes to talk about, of course, is the reinforcement. And that's where the self-driving cars and things like that come into play.
Like a rat getting out of a maze.
That's why NVIDIA's stock price is in an upward slope.
Like
now.
Bitcoin.
Might have been that too. But your talk this morning just...
Till we quantum that thing.
That's right. There goes all my...
All right, so what if we were going into a jewelry store and we're trying to predict the cost of a diamond? So we'll go in, and the jewelry store already has quite a few bits, but we're going to go ahead and fill it out. So we'll have carats along the bottom to determine how large the diamond is, and then we'll figure out how much money it costs on the other side. So this will be great. So now I'll send Ian in. He'll go into the store and he'll start plotting out all the different pieces of the existing diamonds and their costs and where they belong. And so he lines it up. You can see that as they get larger, they get more expensive. It's not a perfect set at all, but it gives you a general feel for it. And now we have our base values that we can start to train against.
Okay, so we're getting into the regression algorithm, right? Let's start diving into this. Now, the next thing is, of course, is that we need our best fit line. We need to understand what line best fits this population of data that we have on this chart.
It's pretty straight.
And it is pretty straight, and it is got a positive slope, right? Because it's going up and to the right.
Now, if you can remember back where the 5 questions that ML can answer, one of them was regression, and the question was how many or when. And so we're going to figure how many. In this case, it's going to be how many dollars.
Yes. So you have cause and effect. Now, the reason we're talking about regression algorithms and getting into algebra here is because I want you to understand a fundamental piece of what deep learning provides. Right? We go into the deep learning, and this, I think, demonstrates it very well once we've kind of defined what's going on in this graph. I'll give you an example of how machine learning, or excuse me, deep learning and neural networks actually figure this tough stuff out. For us, we draw the line on graph paper, we count over boxes, count up boxes.
Yeah, so let's make a prediction.
Okay, so let's make the prediction. And that would be where our y-intercept, if x is 5, our y-intercept is 4.
Because in the future, diamonds are really cheap.
Really $4. $4.
Like the ocean's full of gold.
Yeah, that must be a good bad diamond.
What's nice is, though, look, there is no existing diamond that's that size for us to use as a basis. So this is interesting because we now think we know the value. We think we know what the cost is going to be if we find that's that. And we have a reason to base it off of that, but really we have doubt. There's still not enough because all you can see, some go up, some go down, and they don't really fit on the line.
Yes. So calculating confidence is the area where we get into deep learning. All right. So when I've been writing this stuff, we have a couple of different libraries and tools out there that helps you with deep learning and neural networks. Microsoft puts out a library called CNTK, which is a very nice library. And there is a competing product you may have heard of called TensorFlow, right? And I've been writing quite a bit in TensorFlow, and one of the early things they start showing you how to do this in their docs and things like that is with the regression algorithm. Because again, it's a perfect kind of hello world for this. Where when you're writing this code, typically it's Python, and you're writing this code, you have some variables there representing the line. Okay? And if you're looking at this graph, you might say the line kind of is horizontal and at 1. Right? And then what happens is the machine learning algorithm, once I finish writing the code, it starts out with a line at 1, but really we see that the line should be kind of a 1/2. This looks very 1/2-ish here, instead of 0. So what it does is it runs through a graph, a series of computations. So in TensorFlow, the data flows into a computation or a node. This is why it kind of looks like a neural network here. And then the edges that connect them are called tensors, right? Pretty simple. So you run through this, and all of the edges have arrows pointing to the end of this. And each computation is a little bit of the equation that gets you to the result. So it starts out with this very low confidence in this line that it's giving it initially, and it runs it through. That's called an acyclic directed graph. As you run down to the end of that, you come out with this 0 line that does not match our data. Now, how does it know that? Well, this is where the deep learning piece comes in. It does a least square error, and it drops a count down from each point down to the line, and it tries to minimize that error. So what it does is it takes that graph, that neural network that we have, and it cycles it back to the beginning. Changes those values, moves the line a little bit, and runs it again. Calculates the least square error. Still not good, but better. And it keeps running that loop, that cycle, over and over again. And that's how you get to deep learning and machine learning here. And that's what it's doing. Now, could you do that for some of this for 20 points?
I could do this on graph paper.
Yeah, you could do this on graph paper. But give it, what, 1 billion?
Billion points?
Billion data points?
Maybe two pieces of graph paper.
Okay. Well, that's you.
Yeah. Well, and the idea is this envelope that we put around to determine what the confidence is pretty big here. The more points we add, the tighter we can draw that in. Because you can see one of the points is actually out of it at the top. That would be on purpose. We would do that on purpose, and we would have different algorithms to determine different types of envelopes to be able to pull things out. And the more points we have in there, more confident. So right now it's pretty wide. Right, you can see the 2 points are between 3 and 5, but we think it's 4. That's pretty gigantic. It'd be awfully nice if we thought it was 4, but it could be 3.9 or 4.1. That's the sort of confidence people look for. One thing, I'm sure everybody already knows this, but I'll just say one thing that's obvious. In any type of machine learning project, the goal is never to be 100% accurate, because 100% accuracy basically means you've probably done it wrong. If you can get to 80% accuracy, you've already committed the miracle, right? That's really the dream come true, is right around 80 to 85% accuracy on the prediction from a model.
Yep. And this is exactly what we worked. I work with a company that is doing really cool stuff with golfing, and using these algorithms, we were able to do some really interesting stuff for them. So it's being practically used. Now I'll let you jump into this one right here, because this is another.
There's two types of networks that matter to us. So the first one is the RNN. So a recurrent network allows us to be freakishly good at language so that computers can understand what you're saying. And it's one of the most important use cases for computers, period, when we absolutely know that. That's not what we're talking about here, but it's good to know that this is the other side of the coin of what people really care about. Right? The other side is the convolutional, and convolutional works in a different way, where RNN, or where recurrent networks look at things in series. That's not the way that it works when we're looking at images. In images, we look across the image, and we look across every image in a convolutional array. And so let's You explain CNN to us. Let's forget that RNN exists, but let's remember that it's there. Go ahead. Okay, go to the next slide then. I'll show you. Okay, so let's use me as an example, which I'm happy to do, right? So the first thing, if we were going to figure out anything inside this image, we would break it up into a series of small pixels. So just let's pretend, zoom in on this, and we'll pretend that we have a bunch of pixels here. And the first thing I would apply to it is a filter, or a special type of search pattern, sometimes called a kernel, that would allow me to look at just this, maybe 9 pixels at a time, maybe 18 pixels at a time, whatever the grid is. So go ahead and bring that up. So this is as simple as it might be, where I'm like, okay, I'm starting to recognize there's a couple of patterns here. And this is also, by the way, as simple as a search pattern might be as well. Very simple. Is there a straight line up and down? Is there a line left and right? Is there a corner? Is there a dot? What is it we're looking for? But that's all that I'm looking for. So in this case, I might see that there's a dot, or I might see that there's an edge. You can see all the different things we might be looking for and find there. And now that I've processed that one, I need to go to the next section in the grid. And then the next section again, and then the next section again, and the next section again. And even though this shows that there's possibly 5 things that were found there, in all reality, I would have an individual kernel for each one of those. So that means every section in the grid, I would go against every kernel every time, which is one of the reasons it's so costly to do real-time analysis against video, because once the framework rate starts cranking up, you're really looking at a lot of images fast. Right? That's the hard part.
Right. So to take what he's just explained to you when you're working with an image like this, and we move into what we just learned with the linear regression and how it kind of looks like a graph of computation nodes with tensors or kernels kind of flowing through it. That's the data that's kind of flowing through it. And then it loops back over. When we dive into this piece, that's kind of where this starts happening, where we have the basic image that we hand to the neural network. Once you've handed that over, the first pass that it's doing is it's going in and it's identifying pixels. And then pixels go into edges. Once it's gotten to edges, then it starts looking at the image a little bit differently. And it might take edges and go to corners, right? Then it might go from corners.
By the way, all those different images that you might look at, those actually represent the way that you process images as well. It turns out your brain looks at things just in black and white, then just in green, then just in blue, then just in red. That's one of the reasons certain people are colorblind, because that pass fails. And so they have a color blindness in that color. But we look at the same thing when we do it in a convolutional network as well, because we want to look at each of them individually to start finding the patterns against. When I'm looking at an elephant, I want to make sure that it's against all the other ways I've looked at an elephant before. Just looking at an elephant, you don't try and match is there a big ear or not. That's not the way you're going to find it inside a convolutional network. It's actually going to start finding the patterns, including things. When I look for a face, I'm not looking for 2 eyes. I'm looking actually for shades and the way shadows fall differently depending on where a nose is, where an eye is, things like that.
Yep. So through each pass, you get to these things, right? Right here, we get to kind of the basic shapes of what's in there. And this is where Snapchat starts picking up, right? This is what Snapchat's doing on your phone very quickly, very fast. It's getting to that shape, going from dots and lines to corners, putting those together, getting you to that basic shape. And then it really will kind of understand, okay, this is a face. Now let's overlay a dog. And if they open their mouth, the tongue comes out. You know, these silly kind of things, right?
It's pretty neat how you can start with just such a simple thing. I'm only looking for a line that goes like this, and I'm only looking for a line that goes like that. And then I can take them and say, oh, you have 3 of those, and they go in the shape of a triangle. Let's call that a triangle. And then here, where we're looking at complex shapes, we can say I found a triangle and kind of a hooky thing at the top. But if you find a triangle and a hooky thing at the top, then maybe I've discovered a hanger or some other complex sort of thing I can find. And so it's neat because each one of those relies on the one before it. Right? Because it's not like you see a face. It takes a while, so you can build it up.
Yeah. So that's where training comes into play, right? We've got to actually train the models on a set of data so that it can understand these basic shapes and how those come into complex shapes. Once you've started training the data, then you can start pumping other data through it, or excuse me, training the model. You can start pumping real data through it, and that's where you start getting into classification and other types of things that we see Bing and Google and folks like that do just in search.
Yeah. And as face as an example, it's really nice. Once you know that all the pieces are there, we think this is a face. Now we can go and start identifying things like anchors. And so now the classification is great, but the thing I really need to see is where are the edge of the eyes? Where is the mouth? Which direction is the mouth? Because that doesn't tell you whether or not the person is happy, like that demo at the beginning. We're way far from that still because we haven't even found where the mouth is. Now we can start figuring out where the mouth is, the direction of the mouth, the curve of the mouth, the eyes open, closed, and pieces like that. Then we take that data and feed it to other models that can say, based on the anchor points, we can determine whether or not there is some sort of sentiment or somebody's happy or sad.
Exactly. And that's what we were doing kind of earlier with the camera right here, is that pulls that in. It identifies the face on the machine, or excuse me, it doesn't identify, it identifies the shape,
right?
Ships that up to an emotion API, and our emotion API figures out based on what Jerry was just showing with facial anchors, comes back and tells you, that Jerry's 50.
Yeah, and then, God, that's terrible. I'm not. Not that it matters. One of the reasons we call this deep learning, by the way, is because each one of these steps relies on the one before it, which relies on the one before it, which relies on the one before it. Each one is doing just a tiny little piece, but each one builds on the next. So by the time we get to where are the anchors, lots of things have really executed here. We have a lot of smart mathematicians who have pulled together algorithms to make this more and more efficient and to assume a lot of things. So we're like, yeah, but does it also have a nose? Let's just forget whether or not the nose. We need to put a cat face on our face, on our Snapchat, right? So that just jumps to some assumptions. And when you move, sometimes you'll see the flaw in it, and that's one of the reasons is those algorithms sometimes take shortcuts.
And one of the things that I find interesting, and one of the things we're doing, I think, pretty well at Microsoft is the facial biometrics. We had this before many of other competitors probably have had it out. It's on my Surface Book right there. It was on my Windows phone when I used to have one. Yeah, I was one of the people that had one.
I still, this is my phone. My Windows phone's right there.
With a Windows phone.
I'm a true believer.
But it does, I mean,
I'm a true believer.
Like
what else can we do? All right, we can also take it, now we've seen a face, we can start identifying, oh, you have some of the trademarks in your face of somebody from Iceland. Oh, you have some of the trademarks of other things I can start to discover. So I can say maybe there are indicators there for detailed classification. Maybe even more, I can say there are health indicators. I can say, wow, based on what I'm looking at here, it looks like you are maybe not getting enough sunlight, or maybe even something more serious. Google had just released this where they said looking at just the iris, they are able to determine whether or not heart disease is present. I mean, it's really amazing what we can start to see, because this would be an example of unsupervised clustering, right? Where I can say, here are a whole bunch of eyes of people who are sick. What do you see that's a pattern? And can we look for that pattern anywhere else, right? It's really amazing what we can do, and so much faster. Here's an example of not using vision. So we can do all these amazing things. I can look at all of you, figure out what you're thinking, figure out where you're from, figure out whether or not you're sick. I can even just listen. This is just audio alone, figuring out that this is in an amusement park and near a carousel, and the likelihood of each of those just by listening, because we can use the same sort of pattern recognition that we use in image processing. So it's pretty perfect.
Yeah, exactly. No, it's not perfect. Why? I mean, you got to say it.
Because things are hard.
Okay, so Jerry, Merry Christmas. Here's your cooking robot.
Right. This robot is going to put something in the oven. Right? It's not perfect. What if it's 90% right? Right. Earlier I said 85% was a dream come true. What about 90%? That's still. What about 95% right? No, you just fried your dog. It's a bad deal. Right? So these really matter. So you're like, wow, have we finally cured cancer here? We haven't.
No.
But man, we have come a long way. But let's not forget, I have never put my dog in an oven. On purpose.
On purpose.
Ever. Or accidentally.
We'll talk about why you did it.
Yeah.
At the after party.
Never did.
All right,
so it's neat to step back and talk about some real use cases.
Right. Yeah, because while it's not perfect, and you probably don't want the cooking robot around your dog, there are some very interesting use cases that we've worked on at Microsoft, as well as other companies. So let's start here. I thought this was really interesting.
Ian owns a construction company, and I'm an insurance agent trying to give him insurance, but I won't because there's just too many safety problems. So he shows me this.
Yeah, so I'm Big Brother, right? I go out and put video cameras everywhere, and then I do a little deep learning behind the scenes where I detect all of the different items that I have in my tool sheds on all the work sites or whatnot, and I detect who the people are, because you showed Jerry, the camera recognized that it was me, it recognized that it was Jerry.
Easy. Yeah.
So it sees that this lady walks into the tool shed and she's about to grab a jackhammer.
Now, jackhammers are a very dangerous item, especially from an insurance or construction point of view. Not just anybody should touch them. You have to be certified first. However, Ian's like, hey, Sally is about to touch it, but she's just stepping over it. And so everything's fine. But he's got the same system that if she should happen to pick it up, he could flag that as a problem.
And I could get an alert and call her and say, hey, why are you doing that?
As an insurance agent, this is like a dream come true. This is like as safe as you possibly can be. It's putting your eyes in every possible room. It's pretty neat.
I like this one as well. This has actually got a really good use case instead of helping insurance companies. Saving the white rhino.
That's right.
This is local to you, right?
This is local to me, yeah. I live in Denver. So this is a company in Denver called
there's so many white rhinos in Denver.
World Wildlife Systems or something like that. They're a friend of the other foundation. So they so imagine if you had 100,000 hectares in South Africa and you had on that reserve many white rhinos that you were taking care of. You would put up cameras because it turns out with so little funding, it's just you and a buddy who drive around in a Jeep trying to take care of everything. And in a given day or even week, there are many parts that you will never see, let alone touch. And so here I can put up cameras, increasing the number of eyes that are there, and I'm looking to see the rhino, and I can see the rhino whenever I see it, detect it, and through computer vision, I'm able to see that it's a rhino. I can capture that video and even kind of look at the rhino without having to go in and check on them. But more importantly, I can also detect when there's a person. And so if there's a person in a rhino reserve, and it's not the ranger, then we know why they're there, right? There's just poaching all the time. It's crazy because a single rhino will sell for $200,000. You have to think of the poverty of the place and the motivation of the people, right? It's all there, but the reality is this: there's nothing that can be done unless we just hire an army of people, or we can use computer vision to do it for us. So this allows us to find the poachers quickly.
I just feel like they have like a mission control room, where it's like
It is so
lights up with red.
less high tech than you think.
Let's do that. Now this one hits home with me. I used to be a cyclist. Well, I mean, I still ride my bike. But at one point, I thought I was going to go race in the pro leagues and whatnot until I was injured. And this is really what kind of interested me in this world in the first place. I got injured, and I remember getting wheeled in with a doctor, and there being a robot sitting over there.
Smoking or something?
Yeah, with these tentacles.
What?
Yeah, I mean, that's what it looks like. It's like a robot with tentacles. And then there's this little shed over here where the doctor goes in, and he has computer-assisted surgery. Yeah. And we're doing some pretty interesting stuff in this world.
And this has been going on for a while. LASIK surgery does it this way as well. It tracks your movement of your eye so it doesn't cut your eye off when you look to the side. Right, that's nice. And what it really does is it takes a really, really good surgeon and makes him really, really, really good.
Right.
It's awesome.
It makes park rangers really, really good.
That too.
Yeah. Another one where we're doing a lot of classification.
Yeah. Here's an example of actually in Denver. There's a company that take your picture as you leave aquariums.
Oh yeah.
And they take your picture
too.
Yeah, they take your picture as you leave the zoo, right? All these different things. And they want to group them together. And it turns out you're on vacation. First you go to the aquarium, then the next day you go to the zoo, and the next day you go to the amusement park. Each one of those, they take your picture. The first two you weren't interested in buying. The third one, they want to say, hey, we recognize you from the other ones. We can sell you all three for a discounted rate. Are you still interested? to you, it's magic. To them, that's a business model that really changes things. But it's amazing. And just grouping things together, either through face or just by other categories that you predetermined through some sort of supervised learning.
Any runners or cyclists amongst us? You ever go to the race and then after the race, you know, they said to you, hey, your photograph's up. And you're like, all right, you go to the website and there's 20,000 photographs that you've got to go through.
And you're on dial-up.
Yeah. My AOL account. Here's a picture of my roof. No, not really. This is
Imagine a giant neighborhood. That's a good starting point.
through the hailstorm.
Through the hailstorm.
Right, hailstorm goes through.
I'm an insurance agent again.
And, you know, typically this happens 10 to 12 years after the house was built. When I need a roof. You submit an insurance claim, and all of a sudden, they've got thousands of hail-damaged roofs, and there's 3 or 4 adjusters in the area, right? Common problem. So let's send out the drones, taking the pictures. I think you get the idea there.
And you could do a baseline ahead of time as well.
Yeah, that's true. That's true.
Farming is actually a terrific one, and it kind of is similar to South Africa, where there's so much land. You may have thousands of acres and just not have the opportunity to go to each of the parts of your farm to be able to check on what's going on as much as you would want to. One thing that we've discovered is just the color of your crop can tell a lot about it. And so I can send a drone over your thousands of acres and come back and tell you only the ones that have specific colors, so you can go and check out why they're all turning bright green, dark green, brown, or whatever. And it's really interesting. You really can learn quite a bit just from simple things like that you can easily train custom vision to find for you.
Yeah, I think Martin was working with a company doing that.
Yeah, it's neat stuff.
Up in Redmond.
Shopping. I think we all probably have seen some of the demos and things around shopping.
Jason Bourne.
Great show.
Just skip on past.
We're getting close to time here.
It kind of goes back to making a great surgeon better. So when I look at an X-ray of Ian, I am looking and using it as reference every patient I've ever had in my history.
Yep. And we're actually doing some neat stuff with this, combining that with the HoloLens so that doctors can put the HoloLens on and look at a 3D version of your CAT scan and have the machine learning show them where they should be focusing.
That's because the machine doesn't have my history of patients. It has every doctor's history of patients. So it makes me a super doctor.
I'm not a very fashionable guy, so, you know, it can tell me how to dress, which is, I have a wife for that, though.
Turns out facial markers to be able to identify people follow animals as well. You as a farmer might be really interested in every cow is a $2,000 investment that you have, and you want to make sure nutrition is right. You want to make sure their location is known, especially when it's time for them to have babies and different things like that. Be able to track that. It's really fascinating. Look at 4355.
That's Betsy.
Look at Betsy. She's just a number now.
Yeah, just a number. All right. So, kind of leave you on this note. I think this will say it all. Yeah. This is so much to be done. Do you hear this?
I'm Sakib Sheikh. I lost my sight when I was 7.
Oh, that's better.
And shortly after that, I went to a school for life. And that's where I was introduced to talking computers. And that really opened up a whole new world of opportunities. I joined Microsoft 10 years ago as a software engineer. I love making things which improve people's lives. And one of the things I've always dreamt of since I was at university was this idea of something that could tell you at any moment what's going on around you.
I think it's a man jumping in the air doing a trick on a skateboard.
I teamed up with like-minded engineers to make an app which lets you know who and what is around you. It's based on top of the Microsoft Intelligence APIs, which makes it so much easier to make this kind of thing. The app runs on smartphones, but also on the Pivot smart glasses. When you're talking to a bigger group, sometimes you can talk and there's no response and you think, is everyone listening really well, or are they half asleep? And you never know.
I see two faces. 40-year-old man with a beard looking surprised. 20-year-old woman looking happy.
The app can describe the general age and gender of the people around me and what their emotions are, which is incredible. One of the things that's most useful about the app is the ability to read out text.
Hello, Andrea. This is the menu.
Very fancy. I can use the app on my phone to take a picture of the menu, and it's going to guide me on how to take that correct photo.
Move camera to the bottom right and away from the document.
And then it'll recognize the text. Read me the headings.
I see appetizers, salads, paninis, pizzas, pastas.
Years ago, this was science fiction. I never thought it would be something that you could actually do, but artificial intelligence is improving at an ever faster rate. We're really excited to see where we can take this. As engineers, we're always standing on the shoulders of giants, building on top of what went before. But in this case, we've taken years of research from Microsoft Research to pull this off.
I think it's a young girl throwing an orange frisbee in the park.
For me, it's about taking that far off dream and building it one step at a time. I think this is just the beginning.
No vaporware. That was all for real. It's crazy. Microsoft.ai is where you can find all the services that can do it. And we just live in a good time. No doubt about it. Thanks, Ian.
Thanks, Eric.
Anybody have any questions on computer vision? Yes, sir.
So at one point you had the slide of the young girl with sort of the emotional breakdown. Was that a sort of computer guessed list of emotions?
That's right. That's right. And the numbers next to it was the likelihood that, or its confidence that that is what it was. So that's why there was more than one.
So that list, did somebody like pre-populate, see these are 500 emotions to
That's
pick
right.
from?
Yeah.
Yeah.
It all had to be built from somewhere. That's right.
So it was trained.
That's why Google and Microsoft both are so good at computer vision because of Google.com and Bing, we both have every internet picture there is. So we really have a pretty good seed list. And so we have Microsoft Research, and they have, I forget what Google's research arm is called, but they have a similar sort of thing where that's a lot of labor to cause that to happen. Now it builds itself, but back when there was nothing, it took you and me to do it by hand. That's amazing how far we've come.
And the difference is Microsoft Research allows our researchers to publish.
Yeah. And hey, and you want to know something awesome? Microsoft used computer vision in conjunction with Facebook to find lost children, because Facebook gave basically all its pictures to us, and then we worked with law enforcement to get pictures of lost children, and then we did the facial matching using this and some other systems, and it was amazing. Like it can all be really used for some terrific stuff. Right? It's really great stuff. Yes, sir.
This is all great, wonderful tech. Loving seeing it, and it's inevitable. But I think you and IBM and everybody else doing AI has got to stop, trying to claim that this isn't going to affect jobs. Because I've seen studies that say in 10 to 20 years, 50% of the jobs that exist today will be replaced by machines and jobs.
Yeah, kind of like how the fax machine destroyed the courier business.
No, we're at a much higher rate of disruption. I mean, we've got GM coming out with a car next year with no steering wheel, no gas pedals or whatever. It's going to be used for, I think, Lyft, I think, is their partner initially. So 5 million people in the US are employed by driving a vehicle. So they're all going to be unemployed.
You know what? You're right. You could come up with more examples than that. It is a dangerous tightrope to walk, for sure. Dangerous. Yes, ma'am?
I think there's a lot of hope, though. I mean, at the same time, this has already happened.
That's true. You could think of it as a hopeful side.
This is just adding gas to something that's already existing. Take a look at retail on Amazon. Take a look at.
You know what the largest problem New York City had at the turn of the 19th century?
Horse food.
Horse manure. Horse manure was their largest problem. Do they have that problem today? No.
Manure is still.
I agree with you. the first time I automated somebody out of a job, it hit me that this is real. And NPR just recently ran a whole series on this, automation and people losing their jobs. And it is beautiful, and it's brilliant. And they offered up some alternatives, and we're not here to offer up alternatives to this. I mean, we're not here to solve these problems. But I do like to think about it, and I do like to try and help solve that problem. I think you're absolutely right. And I've heard our CEO talk on it in his book. He shares some of his views on that and what he thinks. And I think he shares 3 main kind of learnings in there. And I think it's, blogged about and stuff like that. So
I mean, on a positive side, we could end up entering into a great age of leisure.
Yeah, or we could help blind people see. I mean, let's not forget the hope side of this.
Oh, no, it's a two-sided.
Yeah,
I see a lot of hope in the future of AI.
Yeah.
And one of the things that strike me as a technical guy is that code is law, right? And eventually these machines are going to operate on people using the codes that they are built on. And one of the things that I see in our society is there's a fundamental flaw here in our society, which I hope to God that you guys correct, because you're at the forefront of this technology. And that fundamental flaw is a very subtle one, and that's called the golden rule. In school, you're told, do unto others as you wish them to do to you. But that is actually a false statement, because the inverse of that statement is true, which is do not do unto other people what you wish them not to do to you. Because if the former was true, then if I was suicidal, then I'd want to shoot everybody, right? Wouldn't that be true? So what I'm saying is, in short,
that's a scary thought.
When you fundamentally have a world system based on the golden rule, which is the inverse of the truth, you have to think how you want to program your machines on the very fundamental basis, and that is giving them not positive, but rather negative instructions. Thou shalt not do the following. Thou shalt not.
Rules.
Yeah.
You see, go back to the 10 Commandments, and I'm not trying to be,
When you're suicidal, you don't want.
There are definitely a lot of.
There might be a built-in presupposition to the golden rule you're
They
skipping,
do
but it's
not
okay.
do to us what they wish not.
When you're suicidal, you don't want other people to kill you.
Yes.
That's not.
So when you categorize people, the things that you use to categorize them are the things that are easy to see or to surmise, such as gender, ethnicity,
Heart rate.
age. And those are also things that are used, of course, to profile people or filter people. That's the negative side of that, is that we have that happening, all over the place already, that people at airports, can be turned away because of the way they look and so on. And the temptation is going to be there, of course, to automate that sort of thing. And in fact, that sort of thing is already being automated. And this, just will make it better. But is it being built into the software some way to program around that? So you could make a thing that could identify a problem without using some kind of broad brush profiling that would victimize people for the way they look.
Well, of course, there's a reality here that people will build whatever they build. We can't build a special algorithm that doesn't do that. People will just build the algorithm that does, right? So, I mean, the question is noble. The answer is impossible, unfortunately. Even if it were illegal, it would be illegally done. Yeah. Yeah. I'm sorry. I follow what you're saying. How can we make this so we don't victimize people who have a specific look?
Well, it's like it's
already done.
So say in a situation you have like an automated job interview, right?
Sure.
Where you have to be racially blind, genderly blind. You have to not know certain things about a person so as not to prejudice the process. It's like it could make something that could interact with a person and find out if they seem enthusiastic about the job without knowing what kind of category.
There's nothing to stop you from building an ethical piece of software. That's for sure.
All right, I think we're good.
That's for sure.
Thank you.
Thanks, everybody.
Nothing except cost.
Cost. It's expensive to be ethical.
Yeah.
Your AI, your video